Visible and I'm audible. So this is Palkin Gupta, PMRF scholar at Department of Material Science and Engineering, IIT Kanpur. And this is the week 3 of NPTEL TA live interaction session for the Rapid Manufacturing course with the course ID of noc22-me74. And the course instructors for this course are Professor J. Ramkumar and Professor Amandeep Singh, Department of Mechanical Engineering, IIT Kanpur. So I hope you guys are enjoying the lecture series, the course contents, as well as these interaction sessions. So there was one question posted in the discussion forum. So I'll go through that first. The question was type. What are the types of scanners that are used in reverse engineering? So what is reverse engineering? Reverse engineering is the process wherein you have the final product first, and using that final product, you develop the CAD models. So in reverse engineering, what you have is initially you have the final product. So it's a very complicated one, and you cannot just have a CAD model by mere visualization. So you kind of scan it using 3D scanners. So 3D scanners aid in giving us the contour and the geometrical information of the 3D objects. What do these scanners do? They aid us in getting the geometrical and contour information. Okay, so some of them are built for short range scanning, while some are ideal for medium or long range scanning, depending upon the size of the objects. If the object is really small, then short range scanning will do. But if the object is large, such as any building or ship, then you need medium to long range scanners. So the build and usage of specific scanners, they usually depend on the size of the object to be scanned. Okay, now uh, the scanners used for measuring small objects, they differ vastly from the ones that are used for large bodied objects. So they are not the same. It is not like you can use the scanner that is used for small objects to scan large objects. So first are short range scanners. These are usually for scanning at a short distance, used for scanning and getting CAD information for small objects. Then we have laser based 3D scanners. What they do is they project a single or multiple laser beams onto the CAD model. So suppose this cube is your CAD model. Now you project some laser beams. So here are suppose 3 laser beams. Now as soon as they encounter this cube, what will happen? They will reflect back. These laser beams, they will reflect, and when they reflect back and come again, they are detected by the sensors here, and that gives us the information about the contour of this object. Now then we have structured light 3D scanners. In these, there is a light pattern that the 3D scanners throw. So it may be in the shape of a bar or a block, and or any other arbitrary shape. So this information is fed to the scanners, and they contain this information about what the geometrical shape of the scanner of the light being thrown by the scanner is. Now this is projected onto the object. When this is project, then there will definitely be reflections. Now and there will be the cutting of the light. Okay, so suppose the light was in the shape of a block and you project it on a sphere. So this is your sphere. So when you project it here, what will happen is, so it will kind of have a contour like shape, this light, something like this maybe. This is your light. So in such a case, what happens is this contour information will be recorded by the sensors, and this will give us the required CAD model. Next, we have medium and long range scanners. So, as I told you, that these are usually for objects such as ships, buildings, aircrafts, etc. What they do is these scanners rotate and spin a mirror. Since the object is really large, so they spin a mirror to distribute the light over a larger area. Now, this reflects the laser outwards towards the object to be scanned, and then the reflections are captured back by the sensors to give us the CAD information. And then there are arm based sensors, or sorry, scanners, or handheld scanners. As you might have commonly noticed during the CT scans of teeth and all, they are handheld scanners that the doctors use. So what they do is they just scan the teeth, and they have that CT scan file or the STL file, which is actually a CAD model file. Okay. So these were the different types of scanners that are used in reverse engineering. I hope I have answered to this query well. Still, if anything is left, you can ask now or again post it in the discussion forum. Okay, so let us now move to this week's lecture content. So, we'll first go through a brief recap of the contents of this lecture. So, this week's lecture talks about modularity, or a design for modularity, which again contains design for manufacturing and design for assembly. So let us first talk about what is a modular design. This term modular is very common, and in the household we have heard it very frequently in terms of modular kitchens. So what do? They just utilize our space efficiently and effectively such that we have enough of storage space, and all our articles are sub, kept there in an efficient manner. Okay, so what same perspective is there in design. What we do is we subdivide a system into smaller parts called modules or skids, and they can be independently created and then used in different systems. So for example, suppose you want to you have a laptop. Example can be taken as your laptop. So you have different components in your laptop, say RAM, the cooling system, the hard drive, etc. These are the different subsystems. Together they perform the function of a laptop, but individually they are subsystems and have their dedicated functions. So these are the different modules or skids for an entire product called laptop. Now, this modular design has functional partitioning into discrete, scalable, and reusable modules. So these are always discrete, that is, they are individual entities. And reusable modules. Suppose if your laptop is worn out now and you cannot use it anymore, but its RAM is functioning efficiently, then you can just take it out and use it in any other system. It would work more or less the same. Rigorous use of well defined modular interfaces. So these modular interfaces, they are used rigorously. So like cooling system, whenever you are doing some heavy work, this cooling system is used rigorously, or hard drive used rigorously for storage purposes, like that. and making use of industry standard for interfaces. So this is basically the standardization of the parts. This helps in cost cutting and as well as easy manufacturing. Since we have industry standards established for this, this will help in easy manufacturing as well and cost cutting as well. Alright. So what are the basically the advantages of modular designing or modularity? Why in the first place we are doing this? To have cost reduction. This is really important because every product that is in their market, it should be affordable. Then to have the flexibility in design. So flexibility in design comes from the fact that the entire product is subdivided into different small parts. So to change the design, you never need to change the entire product, but you can just change some of the components or some of the parts, subparts. Augmentation is like adding new features, addition of new features. Like for a car example, you can have AC as an augmented feature, an add-on feature, or the power steerings or the power windows, and exclusions. So if you do not want a particular feature, you can just exclude that since it is in a separate module. So you can remove or exclude the features that are not of your use. Okay, so these are the advantages of modularity. Now, what are the types of modularity? We have two different types. One is top down and the other is bottom up. So in top down approach, what we do is we have our final product and then we break it down into sub assemblies. So in this, we start from the final product and then go towards the sub assemblies. All right. Okay. Suppose, for example, you have a gear, you want a gearbox, and then you go to sub assemblies of, say, individual gears. How to manufacture those. Now, another is bottoms up. So that is you start from the smaller parts and then go on to build the assemblies. So here you start with small parts and then go on to build sub assemblies and then the final assemblies. Okay, so these are the two different approaches that are usually used in modularity. Okay, so design for modularity is basically has three modules. First one is design for manufacturing, then comes design for assembly, and then is the design of for modularity, which combines both design for manufacturing and design for assembly. So your design for modularity is a combination of both design for manufacturing and design for assembly. So let us see what is design for manufacturing first. So design for manufacturing, it is a technique that is used to ease the manufacturing. So since the name itself has manufacturing, so it is a design technique such that we have ease of manufacturing of parts. So the part should be designed in such a way that the manufacturing is sufficiently easy. Okay, and what are these parts? These are basically the different modules or skids of the final product. So, what is the main aim of this design for manufacturing? It basically focuses on minimizing the complexities, and it reduces the overall part production cost. Okay, it reduces the overall part production cost. So it is giving us two major benefits. That is, it is reducing the complexity. So this would enable us to use sufficiently easy manufacturing processes. And reduces overall part production cost as well. Okay, now, so the process of this design of manufacturing process consists of designing the products such that they have we have to optimize all the manufacturing functions. So all the functions that pertain to manufacturing, that is, first is the fabrication, then the assembly. You have different parts, then you have to assemble those to make the final product. So that is the assembly part. Then you have to test them out to check if they are performing up to the mark or not, to check their functionality. Then is the procurement. So procurement of the raw material or some ready to use parts, subparts. Then once you have the final product, you need to ship it to the desired locations of the customer or your vendors or stock people who are keeping stocks at certain nodes. Then you need to deliver it. Then there is delivery to the specific customers. Then these are after sales operation, but comes under manufacturing since they are directly concerned with the fabrication of the products. With that, there is service for maintenance, or if there is damages or uh, extrapolated damages, and then there is repair when there is an actual damage. And now this design for manufacturing process actually assures us with the best cost, best of the quality, reliability in terms of its functions, and the regulatory compliances, or you can say in simpler terms, the industry standards or the standards set by the government organizations, ensure and to have the best of the safety and to have the least time to market, so that you can have a faster upgradation in the products and the customer satisfaction, which is really given importance these days. Now comes the design review part. We need to review the design on a regular basis so that we can have optimum upgradations and we can have better products. So, the main purpose of this design review is to provide a systematic and thorough product process analysis. Now, this analysis has to be recorded formally. So have a formal record of this analysis and communicate this to the design team for feedback and improvement in the product. Okay, so what we do is we first define a problem, we design it. This is the design review interaction cycle. We define what we actually need. So this is what we define. Then what we do is we design as per the needs what we had set and defined. We design the product. Then we go on to building the product, that is manufacturing. And then we go on to testing, as you have seen car crash test to see if the car is feasible to fly on roads or not. Now, when we have tested it out, we go back to the definition and check if this is what we needed. And then this output is fed to this review change plan or this design review process. So if it is fine and it is up to the mark, we sign off and the process is complete. But if it is not, then this is given as input again to the design team. So this cycle goes on until and unless we have an optimum design. So this cycle goes on operating till we have an optimum design. Okay. So now in design review, we have soft hard reviews, failure mode and effect analysis, and experimental design. So the purpose of the soft hard review is to look into the use of the products in the real world situations. Then they are used to their full capacity. So they basically look into real world conditions. So suppose you are using a pen and it has worn out. So what are the chances of you having any damage from it? Okay, so that is what is soft hard review. Now the next is failure mode and effects analysis. So in this, you describe the parts of the system. Okay, once you have the description, then you list out the possibilities of the failure, like what all failures can occur. Then you list out what is the probability of the occurrence of that failure, and then you list out the if that failure can go undetected or not. So in failure modes and effect analysis, what you do is you first write down the sub parts of the system. Then you list down various failures that can occur. The consequences of these failures. That is the severity, how much harmful they can be. Now, uh, what is the like occurrence, likelihood of occurrence, and then you see what is the probability of uh, this failure occurring. And then you check out the inability to detect these. So we denote them as this as S, then likelihood of occurrence as O, probability of occurrence as P, and this inability to uh, detect is D. So these all are noted down and marks are given according to these. And then it is decided if the product is safe or not, etc. Now we come to experimental design review. So the objective of this is to determine those variables in a process or a product that form the critical parameters and their target values. So this gives us the critical parameters or the parameters that are important to be controlled and their target values, that is what values should be maintained for these parameters. Suppose you have x and y and z parameter. Now you know that this x can lie in this range, this y lies in this range, and this z lies here. So it should not happen that you are maintaining a y value of this range. So this will give you erroneous results, or this would lead to product failures as well. Okay. So that is why experimental design review is important. Okay. Now, why we need DFM, that is design for manufacturing? Because it helps us to eliminate multiple revisions and designs. It minimizes the complexities and as well as reduces the cost of the production cost. Now, since we have seen what is DFM and why we need it, let us check how to perform this. So first is we need to minimize the number of components. So as the number of components would get reduced, assembly costs are reduced, they go down. Then interface failures, they are reduced. Okay, disassembly becomes easier. The service parts become easier. Then use standard commercially available components. For example, nuts, screws, washers. It's always better if we use the standard values of these and not design them of our own. Use common parts across product lines. So common parts. So suppose during the manufacture of automobiles, you have different cars and you want to have tires for them. So you can use tires of same diameter in all of them. It won't affect the functionality much. So use, or this is what a use of common parts across product lines is. Design for ease of part fabrication. We have to design the parts in such a way that they can be fabricated easily, ensuring that there are no complex geometries or minimal complex geometries. We do not go for unnecessary surface finishes. Okay. Now we should design parts with tolerances that are within the process capabilities. So suppose you have the machine can build in tolerance of say zero point 0.5 mm plus minus zero point 0.5 mm. Just a minute. Yeah, sorry. So design parts with tolerances that are within the process capabilities. So suppose the tolerances of the machine that you are using lies within plus minus zero point 0.5, and you design a part that should have a tolerance of plus minus 0.05 mm. So how is that machine supposed to build this? It cannot achieve this. So you need to ensure that what you are designing is compatible with your machine. Design the product to be foolproof during assembly. Sorry. So during the assembly, uh, yeah, the product should be such that when you assemble, it should go in the desired direction only, and they should not be like, oh, this part can be joined here as well and at the other location as well, and then you are just lost where to actually join that part. So all the parts should be such that uh, they they are assembled at desired locations only. Okay, and minimize the use of flexible components like gaskets or belts because they are difficult to handle. Now we next go to design for assembly. Okay, uh, what is an assembly process? It is basically a function of design parameters that are both intensive, that is, they deal with the material properties, and extensive, that is, they deal with the physical properties in nature. Physical properties can be the geometry, the tolerances, surface finish, etc. So these design parameters, they include shape, size, material compatibility, flexibility, thermal conductivity, but it can contain many more and are not restricted to these. These are just a few of the examples. Now, what is the aim of design for assembly? It is the reduction in number of parts and cost reduction. Suppose you have a plate. Okay, then you have a nut and sorry, you have a bolt and a nut for it. So what you can do is, and then there is a hole in this. So what you can do is you can just avoid this nut. This can be avoided. You can just cut out the screws within this plate and fix the nut over there. So you have a reduction of one part. So total number of parts goes from 3 to 2. Okay. So what are the different methods of assembly? Okay. So first is manual assembly. Then is automatic assembly, and then is robotic assembly. So in manual assembly, the parts are transferred to the workbenches where the individual components are converted into final products. Here they use hand tools, and these assemblies are done manually. Okay. So you have actual workers sitting at their workbenches, having tools around them and all the components, accessories that they require. And as soon as the product comes, they just pick up the required tools and the accessories and assemble it into a final product. Then we have automatic assembly. So this method uses a synchronous indexing machines. This uses synchronous indexing machines, okay, that continuously feed the required components to the conveyor belt or to the place where the different parts are being handled. Okay, so this relates to basically the automatic feeding of the parts. Then we have robotic assembly where everything is controlled by the robots. Everything is under control of robots. This makes use of what is known as PLC, Program Logic Controller. Okay, so there are multiple robots on the assembly line. They just do all the job, pick up the components, have the necessary accessories and tools, and just fix all the parts together and make the final component. Now we have different methods of assembly based on type, production volume, and cost. So in this graph, we have assembly cost per product and number of products that can be maintained. So manual assembly has a constant cost, whereas for automatic assembly, the cost per product decreases as the number of products increases. And for robotic assembly, it first decreases and then increases. So we can make note of this break-even points which can allow us to decide which assembly method to use for a particular product. So these points allows us to decide what method to use. Now, next we have based on the annual production volume. So if the annual production volume is, say, these are arbitrary values, just taken here for comparison, say for 100, so we use manual one. So if that lies within this range of 200, so it is one or two robotic arms, and if it lies here, say 500, so it is multiple robotic arms and having multiple stations. But if it is beyond this as well, then there are special purpose automatic assemblies that would do the job. Okay. So we have seen different, we have also gone through different methods during the lectures of the week for evaluating the design for assembly. First one is Hitachi Assembly Evaluation Method from Japan, and second one is Lucas DFA method. And the last method is method based on method time measurement standards, that is MTM standards. Now, after assembly, we go to disassembly. Okay, so as assembly is important, disassembly is also important for the reuse of components, remanufacture, and recycle. Okay, so for these, some of the important reasons we require disassembling as well. So we can either have total disassembly or selective disassembly. So total disassembly is complete dismantling of the product into its constituent parts. So like even single nuts and bolts are taken out as separate entities. But selective disassembly is disassembling only the specific modules. Okay. So for example, you have a laptop, you just disassemble the RAM out of it and keep the hard disk and your speakers and the cooling systems as it is. So that is selective disassembly. So we have the primary producer, then that either manufactures or remanufactures, remanufacturing from used products. So used products are reconditioned or manufactured products are sent to workshop, and then you have the end product. So there is difference between reuse, remanufacture, and recycle. So reuse is you take out a component and reuse it as it is from reuse it as it is in another product of yours. Then you have remanufacture. In this, you just go on to the level of getting the raw materials out of your module. Okay, so in that you just go to the part that you have the raw materials, and then recycle is you get so you get the raw material and develop a new product out of it. Whereas remanufacturing, what you do is you develop the same product as it was before. In recycling, you use it for some other purposes. Now we have process planning, disassembly process planning. So first, for a given product group, we have product analysis. It consists of accessing the end value to be realized. So we have the end value of the product uh, that the product should have, the risk associated with the products or the potentials, as well as the recycling technologies that can be used, how the product can be reused, how can it be recycled, what are the technologies that can be used for recycling and reusing. All that comes under product analysis. Then we have assembly analysis, which concerns with joining of different elements or the assembly part, how they were joined together so that we can understand how to disassemble them, what are the tools that will be required, what forces we need. Suppose you need to turn anything using a spanner, so what force and what time you will be requiring for that. Usage mode and effect analysis, how it was used, how much wear and tear can it endure, how much is the expected life, what are the unexpected conditions that it can just face. All this is usage mode and effect analysis. Then comes determining the disassembling strategy, which is the final part. It can be non-destructive, partially destructive, or the destructive disassembling. This is like very quick, but you get the damaged parts out of it. Whereas in non-destructive, this takes a lot of time, but you get the product as it is. Now, moving on to the last concept, that is modularity and design for modularity. So we had studied about modules. So they are structurally independent building blocks of a larger system with well-defined interfaces. So it is like a RAM cannot perform even the slightest of the functions of the cooling system. So they are independent of each other. Okay, so what are the characteristics of these modules? They form a cooperative subsystem that constitute the product or the manufacturing system, like RAM, cooling systems, hard disk, okay, etc. They work in a cooperative manner to make your laptop work efficiently. Okay. Now, functional interactions occur within the module rather than between different modules, and not between different modules. Okay, so say and a single module can perform one or more. It is not necessary that one module will perform one function only. It can perform more than one function as well. And independent, and they are independent and self-contained and can be combined with other modules to achieve the overall function. Okay, so they are independent and self-contained. So this can be applied to product design, where the overall function can be subdivided into distinct building blocks and modules, or the design problems, wherein you can define how to break down the problem into a set of simpler and easy to manage sub problems Then production systems or the manufacturing systems, how to subdivide the different manufacturing stages, are all of these together. Now we have three phases for design for modularity. First one is decomposition and design for modularity, wherein first we have feature based and variant design. So for example, different colors of the car or your mobile phone. Okay, so one is having AC, one is non-AC, like that. Then you have early cost estimates. So suppose you have decided on the designs, what all designs you'll be having or variants you'll be having. So you estimate an early cost. So okay, so projected cost can be this much. Then you have modular design impact analysis as to see if it is a feasible design, feasible cost, feasible functionality. Now, this all can be clubbed as a classification and for classification and geometric tolerances database for modules and product templates. So these modules and product templates, we have a particular database for them, and these come under the classification for these. And based on this, then we go to codification, that is to develop codes or give different codes based on geometrical, functional, physical or material aspects of this product. Now, for the second part, design for assembly. So, in design for assembly part, what we need is what the customer needs. So, it is basically the customer what how the customer is being satisfied, what all he or she needs, all that. Design for assembly starts with that. Okay, and then based on those we decide what are the target specifications. Okay, and then we develop the product concept for the product. Okay, sorry, I think it got hanged for a while, so I'll just repeat what I just mentioned. Okay. Yeah. So for design for assembly part, we start with what the customer needs. Then what are the target specifications? As per the needs, we define certain specifications of the product and then develop the concept of the product. Now, these are then we go through the design for assembly rules that are standardized, and then we have the final product concept. So when it goes through the design for assembly rules, we then check on if those specifications are in compliance with the rules or not. And also this modular design and impact analysis is also done on this product. And then we have the decomposition of this product to have different modules. Then we go to the design for manufacturing, wherein firstly DFM rules are considered, then cost analysis is made, and then we go to detailed design and prototyping. Now, that was the summary of the lectures for this week. Now, let us go through some of the sample problems that will help you in developing an application-based understanding. So question 1, through dash we can subdivide a system into smaller parts that can be independently created and then used in different systems. So we have been discussing on this since long. So it is modular design. which consists of enabling us to subdivide a component into multiple sub-assemblies that have their own individual functions. These sub-assemblies all have their individual functions that they perform, and they can be used in different systems as well. It is not like if this sub-assembly is for a particular system, it cannot be used in any other system. So they can always be used in other systems as well, depending on their compatibility. So it they should be compatible. Next is, which of the following are the benefits of design for modularity? First is reduction in cost. Yes, this is one of the benefits that we have because of modularity, because we have uh, been able to divide the product into different subparts, which minimizes the complexities, also reduces the cost, minimizes the number of parts. How it is reduced? Because of the reduction of complexities. So because of reduction of complexities, reduction in number of parts, and easy manufacturing techniques. In flexible design, no. We have very much flexibility in designing. We can change even the design of a single part or the module. Inclusion, no. We have the feature of exclusion, of excluding certain features. So the correct answer is reduction in cost. Moving on to the third question, which of the following scenarios can use the concept of design for modularity? In furniture, in computer, in programming of a software, or all of these? In computer, we have been discussing. So in computer, so we have this modularity concept already. So we have different modules: RAM, hard disk, cooling systems, speakers, Bluetooth, etc. displays. They are all different modules. Now, in programming of a software, yes, we can have modules in these as well. As you have seen in certain paid softwares, or say certain CAD modeling softwares as well, or simulation softwares. Examples. So you have certain modules that are available to you for free. So for simulation, let us say example of structural analysis they have. Then they have explicit dynamics analysis. Then we have thermal analysis. So these are all different modules. Operating structural analysis won't affect in any way the thermal analysis. So it is the backend programming of these softwares that helps us with these. Now in furniture as well, we are having modular furniture, as you might have heard. So wherein we can just extend the dimensions of, say, the table as per our needs. We can extend the length of the table. as per our need, or we have sofa cum beds, so we can use them as sofas or beds. They are different modules. So the correct answer is all of these. Next question, question 4. Dash is a design technique for manufacturing ease of an assortment of parts that would constitute the final product after assembly. So here we are talking about manufacturing. So the options are design for modularity, design for assembly, and design for manufacturing, or none of these. Here we are talking about this design technique for manufacturing ease. So the correct answer is design for manufacturing, which looks after the manufacturing of the parts. Design for assembly looks at the assembling and disassembling part. So this is majorly concerned with the assembly and disassembly. Okay, and design for modularity. This is basically subdivision of a particular product into multiple number of smaller products. So design for modularity, this is subdivision into smaller parts. So next we have question 5. What is or are the advantages of design for manufacturability? First is optimization of all the manufacturing functions. Yes, this is one of the advantages, and we have discussed in detail, wherein this contains fabrication, assembly, test, procurement, service, repair, etc. Assurance of best cost. Yes, this is if we go on to design our parts using design for manufacturability, we are assured the best cost and the safety as well. So, correct answer will be all of these. Next question, question number 6. Which of the following can be the purpose of a design review? First option, to provide a systematic and thorough product process analysis. Yes. As the name suggests, design review. We review the design, check if it is within design limits and it is up to the target specifications or not, and if it is performing its functions well. If it performs the assigned functions well. Okay. And the a formal record of the product process analysis. Yes, every time the analysis is done, a formal record has to be maintained so that you can always look back so that in future you can always look back what were the weaknesses of a particular product or the strengths of a particular product, and then feedback to the design team for product and process improvement. Yes, if this feedback is not given, how will there will be an improvement? The design team cannot improvise on the product and the process without any feedback. So the correct answer is all of these. Question number 7. Dash addresses the need to design a product for safety in terms of the real world condition. Soft hard review, team review, management review, or none of these. So, what was soft hard review? We had discussed it during today's lecture as well. So, soft hard review concerns with uh,
the safety or the use of the product in real world situations. Use of the product by the users in real world conditions beyond their wear and tear. Okay. Next is team review. So this is basically the review of a team, and next is a management review. The correct answer is soft heart review. This is one of the design review processes. So other two processes were, as mentioned, failure mode and effect analysis, and the other was experimental design, and one is your soft hard review, with on which this question is based. Now, question A: which of the following risk indices is are associated with failure mode and effects analysis? So we had seen we had certain indices. So were those indices? We had four indices in total. So first was the consequences of the failure. That is the severity. If that failure affects too much or not, or really harmful to the presence of the human or not, or like if that defect is there or failure has occurred, so it won't affect the human life at all, like that. Then we had the likelihood of occurrence of that failure. How much is the possibility? Now we have the probability of occurrence of the failure, and then last we had the inability of the control to detect it, if at all that failure can go unnoticed. Okay. So, in options, I can see severity, likelihood of occurrence, probability of occurrence. So, all of these are the indices which are associated with failure modes and effect analysis. So, question 9: the objective of an experimental design is to determine those variables in a process or product that form critical parameters and their target values. Okay, so experimental design, this is one of the design review processes, is to determine those variables or those critical parameters and their target values. Okay, so this is true. Experimental design is wholly based on the critical parameters of a process or a product. The last question is: design for manufacturing methodology allows for new or improved products to be designed, manufactured, and offered to the consumer in a shorter amount of time. This is very much true. So this design for manufacturing methodology, this has helped us to divide the product into small subparts or modules. Now, having improvement in design in single modules is easier than having improvements in the entire product all at once. So that is why we have a short time to market, or shorter time to deliver the products to the customer. So these were the questions for today and the summary of the week's content. So I hope the questions are clear and the content is also clear. So if you guys have any doubt, you can always post them on the discussion forum, and these slides and this lecture video will be available to you through Google Drive links and YouTube links. So I think if anyone has any questions, we can take them up. Okay, so I'll just end this session. Thank you all for joining in.